Date 2024, question 39. A solid slab of thickness H1 is initially at a uniform temperature T0. Let's say this is my solid slab. So this is my solid slab, let's say, of initially uniform temperature T0. So mathematically we can write at T less than 0, 0 less than y equal to y is shown. That means all over this body here, T1 is temperature is equal to T0. Here, uniform temperature T0. At time T is equal to 0, the temperature of the top surface at y is equal to H1 is increased to T1. So, at temperature T greater than equal to 0, at certain time, at y is equal to H1, that means it's my top surface, I increase the temperature T is equal to T, while the bottom surface at y is equal to 0 is maintained at T0 for T less greater than equal to 0. What happens at y is equal to 0? So at temperature T greater than equal to 0, T remains T0. So what is really initially, so what happens initially, the entire thing was at T0. At a certain time, T greater than equal to 0, I increase this temperature to T1 while this temperature is remaining constant at T0. Okay. So of course, there will be a heat flux along this direction. Now it says assume heat transfer occurs only in the y direction. Of course, if I put the y this way, there will be a negative y direction heat transfer. And all thermal properties of the slab are constant. The time required for the temperature at y is equal to h1 over 2 to reach 99% of the steady state value is T1. So what is happening? Assuming at steady state, that means at time T tends to infinity, a very long time, at y is equal to h1 over 2. So this is right here, which is of course the center line of this particular slab here. Let's say T is equal to Ts, which is the one is the time when the temperature reaches the steady state temperature Ts. Okay. If the thickness of the slab, now this is the second situation, if the thickness of the slab is now increased or double to H2 is equal to H1. So now we take a slab which is of double thickness than this one. So whatever is thickness, so H2, if the thickness is H2, so H2 is equal to 2H1. Otherwise, the conditions remaining the same. That means at initially less than 0, all over the body here, the temperature was equal to T0. At time t greater than equal to 0 at a certain time, right at the top surface, we have increased the temperature to T1, while the bottom temperature is remaining constant, y is equal to 0. This is the condition. Now, this is my center line here, middle of the slab. Let's say the temperature, so the tau 2 at time tau 2 it reaches the same again steady state temperature, let's say Ts here. So what is the relationship between tau 1 and tau 2? That means we have to find out tau 2 over tau 1. So how do you solve this problem? So of course this is a transient heat conduction problem, because initially at a certain temperature, now we have increased the temperature along the y direction. The end surfaces are kept at the same temperature for both the cases. At certain at y is equal to h1, and for the next case, y is equal to h2, temperature has been increased to t1, and always at y is equal to 0, that the bottom surface remains at the initial temperature. And we also say H2 is equal to 2H1. So there is a dimensionless transient temperature, which is given, of course, in gene copy. And of course, details are given in unitoperation.com. This is the equation, transient equation, where theta is the dimensionless temperature, which is this one. N, of course, is the integer. Depends upon how much accurate result you want. If you increase the value of n, that your result will be more accurate. And this is, of course, a sine function. And n already we have said. And y over h, of course, is a dimensionless height. And here f4 is the Fourier number, which is alpha t over h square. Alpha is, of course, the thermal diffusivity. Since theta remains the same for both cases, so this would be the same. And we are looking in the middle of the slabs in both cases. Initially for when we had the thinner slab, and then we have a thicker slab. So we are looking at the center line. So this y over h remains the same. So basically, what you see, the Fourier number will also be the same in both cases. If that is so, if the Fourier number is identical for both the cases, we can write the Fourier number. As I could see, that tau, of course, would be proportional to h. So if we do the calculation, this becomes, because this is 2h2 is equal to 2h1, so the ratio would be equal to 4. So what we're going to say that C, of course, is going to be the correct option.